Okay, this is practice midterm number 3, question 5, the last of the written problems. And the question is, or the problem is, draw the Lewis dot structures for the following compounds with proper geometry, and open parentheses, include resonant forms, close parentheses, assign formal charge to each atom. And so we'll have to denote that unambiguously on the page. And A is phosphorus pentachloride, PCl5. B is the arsonium, or arsenic trihydride, ASH3, the arsonium molecule, arsonia, I should say. Arsonium would be with positive charged ion. C, silicon tetrahydride, or silane, as it's known, is similar, is the analog of methane. It'd be silane. And D is sulfur dioxide, denoted as SO2. E is iodine pentafluoride, denoted as IF5. And F is carbon dioxide, denoted as CO2. So, I'll do the scratch paper part on the page, erase it, and put the final result in. We have to go through several stages when we're doing the Lewis dots. First, find the Lewis dot form, then count the bonding pairs and assign the proper molecular geometry, which we can then draw, and then last, assign the formal charge to each atom in the process. So we start with phosphorus pentachloride, and the way we do this, or the process, the procedure which we always faithfully follow the sequence, as I start by placing the unique atom at the center, and then I'm going to surround it with the outer atoms. So I'll start with a phosphorus atom surrounded by 5 chlorine atoms, and I will add up all the electrons, the valence electrons in the compound. So I have 1, 2, 3, 4, 5, and chlorine is group 7A, so that would be 5 times 7 plus phosphorus is group 5. 5 times 7 plus 5 equals, well, this is 35 plus 5 equals 40 electrons. Now, I will draw a line from the central atom connecting it to the outer atoms and depicting a bonding pair with each. I will deduct the 2, 4, 6, 8, 10 electrons from the total count. Minus 10 electrons gives me 30 electrons remaining. Now the next step is to assign all of these 30 electrons pairwise, distribute them pairwise to the outer atoms, completing its octet of each. And then if there's any electrons left over, we will place them pairwise on the central atom before we go check. But right now it's a simple matter of how many each of the outer atoms in this and every compound we're going to draw from now on. The outer atoms are going to be 6 electrons short of an octet. So that means 6 electrons times 1, 2, 3, 4, 5, which is going to take all 30 electrons, 6 times 5 being 30. So I'll distribute those 1, 2, 3, 4, 5, 6, 7, 8, projected. So I draw the 30 little freckles there, minus 30 electrons, and we're done. So I am now done drawing a proper Lewis structure. I can erase now. This is all scratch paper work I'm doing right now. So I'll erase this. And now I'm going to look at the molecule and determine how many electron pairs are associated with the central atom only. So now I have to determine how many of those pairs exist, and you count, when we're counting bonding pairs, a single bond is the same as a double bond, is the same as a triple bond. Counts as only one pair. Oh, well, first, no, let's finish Lewis. Lewis, have we satisfied the octet rule all around? Yes, indeed. I have an octet with all the outer atoms, and I have 2, 4, 6, 8, 10 electrons associated with the phosphorus, the central atom. Well, it turns out for the third row elements and beyond, third and higher rows, we can expand our octet because size is important. They are large enough to accommodate more than 8 electrons in their shell, their bonding shell. And so we have an expanded octet. We've satisfied the octet rule here. This is not a violation. And so this is indeed a Lewis structure, and now I need to count the pairs associated with the central atom, and there's 1, 2, 3, 4, 5 such bonding pairs. And since that 5, we know from 5 electron pairs demands trigonal bipyramidal electron pair geometry, and there are no lone pairs on the central atom. Therefore, the electron pair geometry is going to be the same as the molecular geometry. So I'm going to end up with the trigonal bipyramidal molecular geometry and D-pair geometry. So now I can redraw the molecule with the proper geometry. And that I will take and place chlorine and phosphorus, chlorine, taking up the axial positions of the trigonal bipyramidal geometry. And I'll place the lone pairs on each of those. Now I have to deal, those are called the axial positions and the trigonal bipyramidal geometry. Now I can place one chlorine out here with its resulting lone pairs, and the other two, and these are the equatorial positions in the trigonal bipyramidal geometry. I'll place a chlorine atom here coming out of the board. So we have to be able to depict a three-dimensional object on a two-dimensional surface. So I'll use the wedge to denote the one that's coming out of the board, and a dashed line to depict the bond that's going into the board. And I've now completed that part of the question. I have drawn the molecule with the proper molecular geometry. So this would be on my permanent answer. And now I have to unambiguously assign the formal charge to each atom. And this is a simple matter of I divide the shared electrons equally. So for each bonding pair, I'm going to give 1 electron to chlorine and 1 electron to phosphorus. And after having divided those in that fashion, the formal charge is going to be equal to the group number of the element minus the number of electrons, since the electrons are negatively charged. And so this gives me 1, 2, 3, 4, 5, 6, 7 electrons with chlorine, and the group number for chlorine is 7. So I have the formal charge, this is scratch paper. For chlorine, it's 7 minus 7 equals 0. So I have 0 formal charge on chlorine. Now it's going to be the same for all the chlorines. So now I have to assign the formal charge to phosphorus. And I've got 1, 2, 3, 4, 5 electrons with the phosphorus, and phosphorus is group 5, so it's 5 minus 5 equals 0. So I have 0 formal charge on the chlorine. Now, I want to depict this on the page with the formal charge assignment in an unambiguous fashion. We can do this several ways. The clearest that I can think of is, I'll erase this scratch paper work. I could either draw the formal charge on over each atom like that, but personally I don't like that approach, because with all the dots on the page, that can easily be confused with a lone pair, particularly when you're in a hurry on a test. So that wouldn't be my first choice. A better way to do this is to have, for phosphorus, I'll put, and chlorine, I'll put the formal charge is 0 and 0. You know, for each, there's 0 for each of the chlorine atoms. So I'll say, I can write atom, formal charge. And this way I can unambiguously assign it, and there's no doubt as to what I mean. So I'm going to erase this information I have in red for this approach. This is unambiguously doing it that way. And in the event that we end up with a molecule where there's distinct types of atoms, there's more than one type of chlorine atom, or in this case I could say equatorial and axial, but this is not, there's no difference in formal charge. So this is for each chlorine. I would number the atoms and then say, in the event that there was inequivalent atoms, then I would number them and then give the formal charge in a table like this over on the right-hand side. And so that answers that question in as clear a fashion as I can think of. And that would be the most acceptable approach. Now let's do the same thing for arsenic trihydride. And we'll start with, we'll do this in red again. This is my scratch paper. I'll start with the arsenic atom at the center. I'll surround it with hydrogen atoms. I will now add up the electrons present. I have 3 hydrogens group 1, 3 times 1, plus, again, 5 for group number of arsenic, equals 8 electrons. Okay, so now I will draw a line connecting the central atom to the outer atoms. And I will deduct 2 electrons for each of those. So that is minus 6 electrons. There are 2 electrons remaining. That's 1 pair. So the first thing I do is I distribute this to the outer atoms in order to complete its octet, to give it that closed shell noble gas configuration. I'm using the word octet very liberally here because in the event, in the case of hydrogen, it's a first row element. And its closed shell configuration has 2 electrons, not 8. So it's already achieved the noble gas closed shell structure. So I've already completed the outer atoms, so this remaining pair of electrons has to be distributed to the central atom. And you always do this before you start debating whether or not we're going to form a multiple bond. We'll see an example of that shortly. And so now, having done that work, I want to determine whether or not I've satisfied Lewis dot constraints or Lewis dot demands. And the Lewis dot demands that each atom in a compound attains the closed shell electron count that is commensurate with the noble gas in that row. And in other words, the octet rule. And I have 2, 4, 6, 8 electrons associated with arsenic, and I have 2 electrons associated with each of the hydrogens. So indeed, the Lewis dot constraints or demands are satisfied. So now we can draw the molecule with the proper geometry. This is going to have, now I'm counting the electron pairs in terms of the central atom. And I have 1, 2, 3, 4 pairs of electrons associated with the central atom. This is going to demand tetrahedral E-pair geometry. But in this case, there is one lone pair of electrons on the central atom, and so in this case, the electron pair geometry is not going to be the same as the molecular geometry. The molecular geometry is going to be that arises when we place the lone pair of electrons in one of the positions and the atoms in all of the other positions of the tetrahedral positions. And so I'll draw that right now. I'll take the lone pair and place them here above the arsenic. In one of the tetrahedral positions, I'll place a hydrogen. I'll draw the other two hydrogen atoms in the other 2 tetrahedral positions, one being coming out of the board and going down, the other going down and going into the board. And I draw that with a dashed line. I have now got the molecule with the proper geometry, and this is, by the way, called a tridentine pyramidal molecular geometry, while we have tetrahedral E-pair geometry, the distinction we're going to need to take into consideration when we start determining what type of hybridization we're going to observe with the arsenic. But in this problem, we're done. This is the proper geometry. There is no resonance forms required. And so now all we need to do is assign formal charge. Well, you can see, and I'm just going to go over here and make my table. And so the atom and formal charge. For the atom being the arsenic, I have 1, 2, 3, 4, 5 electrons, and it's group number 5. 5 minus 5 is 0. So I have 0 formal charge assigned to the arsenic. And I have, for the hydrogens, I have 1 electron each. They're group 1. 1 minus 1 is again 0. So we have the, again, spectacular distribution of formal charge. 0 formal charge on each atom. And please note, as a check, if I add the formal charges, they have to add up to the charge on the molecule. And in this case, the molecule is neutral, and the formal charges add up to 0. So that passes that check. This completes what I would expect you to have on the test for this particular problem.